Our Math 2413, day 27, 05, 01, 23. Last week of classes. For you, what do you think integrals are? What did we do with first derivatives? What do they find for us? They find the slope. What else do they find for us? The maximum is the vertices, the maximum. Second derivative finds concavity, point of inflection. It also helps us find from motion problems, from position to velocity to acceleration. That's all getting faster and stuff like this. Now we're going backwards. Here, with integrals, the function I give you will actually be the derivative. When you take the integral, you're going to tell me the function it came from. That's the goal of this chapter. A little bit more so, which is the crux of this stuff. Let's pretend we had a function. Minus x squared. What would that look like? The V shape?
No, the little parabola.
Exactly.
But it flipped over.
Because it's an x squared, it's a parabola. It's negative, it's opening down, and it's shifted up one. It looks something like that. Now, in this section, our objective is to find areas under a curve. This is 1/2. This is 1. It's 1 and 1/2, 2. Because this is pretty much where the rest of the calculuses take off. We end finding areas of under curves, any type of curves. And then we start rotating them about the y-axis, about the x-axis. And then in calculus 2, we start looking at 3 dimensions. We can find surface areas. We can find areas of solids in 3-dimensional space. So for us right now, I want to look at this function. How would you come up with a way of determining the area of this region? I want the area of this region. Well, the formula for area, yeah, is base times height, right? But, okay, what would be your base?
X.
But what value? Okay, what's your height? 1 times 1. So you're saying this area is 1. Even though, if we drew a rectangle, which is what an area is, it's a rectangle. Is that a true area? No, because we have all this wasted space right here that we are paying for we don't want. So let's think of another plan. You're right. That's the way it would be started off originally. What would be another way? How would we go out and fix this? Yes. Using what function? That's not a unit circle. You guys are talking about saying you could, but it wouldn't give you the right answer. Because can you use this equation? It's not a complete circle. Well, you could have. You could have taken this, find the area, divide by 4, but it wouldn't give us because this curve is not the same curve as what the formula would give us. This formula would give us the values themselves now are at a magnitude off the square root part. So we'd still be off. Let's think of another way. A real-life example of this is you're designing your house. You have a table. You want one part of your actually. Let's say you want to do something here. You want to put some special material on top of your table at this corner. How much would you need? How much material would you need? It's super expensive stuff. I mean, you could go out and buy one of these and keep on chopping it off until it fits. You waste all the other space. We're still going to use the rectangle concept. How else could you do it if you use the rectangle concept? Okay? So that first way is not good. What if we made 2 rectangles? Is that better? Well, yeah, because the first rectangle would have been all over here. We're now saving this much, so it's a little bit better. If that's a little bit better, how can we make it even much more better? We've gotten rid of a whole bunch of more stuff in there. So you see what's going on here? We're partitioning the domain, the width of this object. Instead of making one big cut, we're making it down 2 cuts. We're getting better. So we make it into 4 cuts, or 3 cuts in 4 sections. What would happen? What would happen if we had it in 1/116th? So you have 15 little boxes in here. Wouldn't that be more accurate? Yes, but it'd still be over. It would still be over because if you zoomed in on this thing, you're looking at this again. So is there another way we could do it? We're still going to look at the 1/2. We're first going to build up this one. we did it last time. What if we work backwards? What if now we work from this side over? What's wrong with that method? Well, it's a lot short, because if we go from the right-hand side and go left, we're missing all of this area. And even if we look at it cut up even more, 1/4, 1/2, 3/4, 1. That's a little bit better. Now we have more of the area taken care of, but we're losing this area, we're losing this area, and that area. So what's happening here? We have one method that's too small, because we're missing all this area. And then we have another one that's too big. The true area is somewhere between there. Can you think of another way we could do this? That would get us in the middle somewhere. I gave you the clue in that sentence. Can you think of a way, a method we can use to get us in the middle there? More time? No, we're not. We haven't found any tangent lines. We haven't taken the derivative of anything. I just gave you the curve, which is y equals 1 minus x squared. And from there, this is all algebra. Because all we're doing is building these rectangles. We have the concept. The more rectangles we build, the more accurate it's going to become. But this one won't be enough. It'll be less than the actual area. This one will be too much. And how do we find the area? Once we do all these, even with a lot more, how do we find the area of those pictures? So what's the area if I had these 4 boxes, or these 4 boxes? This is area 1, area 2, area 3, that one's gone, area 1, area 2, area 3, and this is area 4. How do we calculate the area of this first one? Remember, the area of this first one is the area of the first one plus the area of the second one plus the area of the third one. The area of the first one, the area of the second. Remember, each one of these are the function itself times the width. So the only thing changes in this formula. does f represent? So f is the function 1 minus x squared. What does w represent? The width. How do we find the width? This is x sub 0, x sub 1, x sub 2, x sub 3, and this is x sub 4. The width is x sub 3 minus x sub 2. X sub 2 minus x sub 2, those should all be the same. So we call that delta x. So the delta x for all of these should be the same. How do we calculate the height? Remember, the formula for the area is base times height. The base is the width, which is delta x. And the height has to be the function. So what's the only thing that changes in the function? Your input. What x are you putting in there? So in this first one here, in this left side, we have x1, x2, x3, x4, x0, 1, 2, 3, 4. So how do we figure out the height of this one? We know that w is 1/4 of an inch, or 1/4 of a unit. How do we figure out the height? What x value are you putting in there? Let's look at this one here. We're going from the curve to there. So the first one, we'd pick x1. So this would be f of x1 times delta x. Then the next curve starts off at x2. So it's f of x2 delta x. F of x3 delta x, and f of x4 delta x. Even though this one's going to give us 0. Why would this one give us 0? Remember, it's at 1. If you plug that into the function, what's 1 squared? 1 minus 1 is 0. So that's why this one doesn't have any area. So you add up all those areas, and you have this area. This is A sub I, capital I. I'll tell you why in a second. Now this one, what x do you put in this one? Here's x sub 0, x sub 1, 2, 3, 4. So what's your input in this other one? Look at the box. What's the highest of the box? Does it belong to the x0 or does it belong to x1? Where is it touching the curve? It's touching the curve up there, right? This one's out here dangling. So this is the one, that's the input. It's at x0. The next box, where is it touching? at x1. It starts here. So this is f of x1, delta x. The third box starts at x2, delta x. And the last one is f of x3, delta x. Now, what we're looking at here are these two pictures. If we start on the right side of the interval, we have a small area. If we start on the left side of the interval, then we have a bigger area. So that's why this is, when we add these together, this is called the lower sum. It's called the lower sum. Because out of this inequality, it's the smallest of the three. So what do you think this one's going to be called? That one's called the upper sum. So upper sum is taken, in this case, is taken on the left end of the interval. The lower sum, because it's a decreasing function, is taken on the right-hand side of the interval. These guys have other names. They're called inscribed and superscribed. Inscribed because the picture is drawn inside the function. Superscribed because it's got part of it outside the function. Superscribed, always the upper bound because it's got wasted space. Inscribed is the lower bound, lower sum because it doesn't. So let's do some calculations. Our function is still this. Our domain is still this. I want you to use four segments. You're going to cut it up in 4 pieces. And find the areas. At least write down the formula for it. Work out the numbers. Let me help you get started here. So, always draw your picture. Our bounds are between 0 and 1. I take 0 to 1, divide it by 4. Have 4 equal segments. So 1 divided by 4 makes it, this is 1/4, 2/4, 3/4, and 4/4. 2 over 4 is 1/2. So these are my input values. These are my x's. So when you answer these first questions in section 1, you have to figure out, okay, how many divisions will I have to deal with? Those are your inputs. What you're going to do, you're going to input those into the functions. So it's going to be f of 1/4 plus f of 1/2 plus f of 3/4 plus f of 1. What are we looking for here? We're looking for the area underneath it. So what we're doing is we're finding the areas of all of these interior boxes and adding them together. So the inscribed area, so my W, my width, or my base, for base times height, let's call it base, for base times height, is 1/4. So I have f of 1/4 times 1/4, f of 1/2 times 1/4, plus f of 3/4 times 1/4, f of 1 times 1/4. This is my height, this is my y value, this is my x value, base times height. So, if you put in 1/4 into your equation in here, one minus 1/4 squared, 1 minus 1/16 is equal to what? The rule for subtracting fractions is they have to have what? So this 1 is the same thing as what? Common denominator is 16, so 16 minus 1 is 15. So it's 15 over 16 times 1/4. That's for this first one. Then you put 1/2. 1/2 is squared is 1/4. 4 over 4 minus 1 over 4 is 3 over 4 times 1/4. Then 3 over 4 is 9 over 16. 16 minus 9 is 7 over 16. At 1, 1 minus 1 is 0. Sorry for my handwriting. These are 4s and 16s. There's no 9s anywhere there. Well, the common denominator is going to be 64. 15 times 1 is 15. This one needs a 4 over 4. 12 over 64. 7 over 64. 27. 34 over 64. That's the summation of those areas. That's the inscribed area. Do the same thing with the superscribed area. It's pretty hard to do math without writing things down. What's that?
Do you simplify it?
Well, yeah, of course you simplify it, yeah. But I'm just saying, at this point, yeah, use a calculator, because just type all this stuff in and hit enter instead of, because this is very, you wouldn't be happy with this. So you'd make it, instead of 1/4, you make it 1/8, and then 1/16, and 1/32, and 1/64. So yeah, you'd always keep on because that's eventually where we're going to get to. We're going to get to a point where we're taking a limit of these as x goes to 0, as the difference between the bottom, the width of it becomes 0, so we have the actual exact area. So yes, we're not away from limits yet, because we have to still do it to find these areas. But instead of here, we're using now something called, we're going to call it sigma notation. So this is all lower sum. Let's do upper sum, the same information. Between 0 and 1. The base is 1/4. Function is 1 minus x squared. Remember, for the upper sum, we're taking the left, and since it's a decreasing function, we're taking the left bounds of each subinterval. Put the same notations there. So our x's are going to be 0, 1/4, 1/2, and 3/4. Of 0, 1/4, f of 1/2, f of 3/4. Superscript area is f of 0 times 1/4, f of 1/4 times 1/4, f of 1/2 times 1/4, f of 3/4 times 1/4. Remember, this is your base, this is your height. That's the formula for an area. So at 0, what's our function? 1. X is 0, 1 minus 0 is 1. At 1/4, we have 1 minus 1/4 squared, 1 minus 1/16, which makes it 15/16. One minus 1/2 squared. 1 minus 1/4. Is it 3/4? One minus 3/4 squared. 1 minus 9/16. 7/16. We have to have common denominator is going to be 64. So this one needs another 4/4. This one needs a 16/16. 16/64. 15/64. 12/64. 7/64. Plus 15, plus 12, plus 7, 30, 41, 50/64. We've narrowed it down. We know it's got to be between 34/64 and 50/64. Yeah, again, we can simplify the denominators. We can simplify it even further. So how can we get even closer? Can you think of another method to get us even closer? Using rectangles? This. Because you know, if we use the left bound, we have too much wasted. If you use the right bound, you have not enough counted. What if these were the midpoints? When we did the graph itself, the rectangles look like this. They're still going to be the same width, So 1/4, 1/2, 3/4. The rectangles, they're still going to be the same width. It's just that now, in this delta x, we have to find the halfway point, the midpoint, and use that as our input. So in this rectangle, I'm going to make the rectangle so that this value here is my input. So that's half of 1/4, so that's 1/8. The next input would be at 5/8. So you're letting the inscribed and the superscribed cancel each other out. And the more narrow delta x is, the less actual waste you have. So let's look at what that would look like. The width is still going to be delta x, but now we're only looking at that value. So our f inputs are 1/8 times 1/4. That's eighth. F of 5/8 is 1/4. And we have the next one. And this is 1/8. And I'm sorry, it's 3/8, not 5/8. It's 3/8. This next one is 5/8. And that last one is 7/8. So it's 1/8, 3/8, 5/8, and 7/8. These are my midpoints. This is called the midpoint method. Or the midpoint rule method. Because you're keeping the width of your rectangles the same, you're just now, the height of it will be the midpoint of the upper and lower bounds. Upper and lower sums, I mean. So let's see what this one looks like. The function's still the same. It's 1 minus x squared. So we have, for the first one, we have 1 minus 1/8 squared over 64. So 63/64 is this one. Times 1/4. Nine over 64. $55/64. Then 5 over 8 is 25 over 64. So 64 minus 25, 39. 64th times 1/4. And 7/8 is 49 over 64. 64 minus 49 makes it 15. $18, $857, $182 over 256. This is the area of the midpoint method. Now we're getting a lot closer to the actual area under that curve. Yes, you see, this is the same thing we did in Chapter 2. To find the limits of a function, we have to do all this work. The epsilon delta stuff. We're doing the same thing here. When I start showing you the shortcuts for the integrals, we'll be done already. But we have to know what it means, where it comes from. So what we have is we have the inscribed area, midpoint area, the actual area, and the superscribed area. So this is the closest we can get right now. This is only using 4 rectangles. If we want to be accurate, we'd have 1,000 rectangles. Even that would have an error factor. So the more rectangles you have, the more accurate your answers are. Which is why we use programs, like we can even use Excel for this. Just keep on doing this formula over and over and over 1,000 times. We're going to do that. So, what does this method show us to do? This method shows us that we could take any area, any object, and cut it up into pieces, partition it, and get closer and closer and closer to the true answer, to the actual either area or volume or speed, whatever we're looking for. Let's look at a motion problem. Example of a motion problem. Is velocity always constant? So if an object is moving on a straight line from x sub 0 to x sub, let's say 1, or x sub n, that's the final point. In order for us to find out the true speed or distance traveled by this object, we have to break it up into pieces. The formula for distance. Distance is a factor of time. What's the formula for distance? You're in your car. Your speedometer says 60. And you've been driving for 1 hour. How far have you gone? 60 miles. Because your speedometer is read as what? 60 miles per hour. Miles per hour. So miles is the distance. Hours, this is called the rate. This is your speed. So since miles is your distance, hours is your time. So you have your distance over your time times rate. So distance, if you multiply t to both sides, distance is calculated by rate times time. Rate is a factor of time times time. The time traveled. So in order what you have to do, you'd have to subdivide these distances. This is distance 0, this is distance 1, distance 2, distance 3, distance 4, distance 5, and distance 6. You have to find each one of those, add them together, and divide by how many you have. That would tell you the average rate of speed that you've been traveling from point A to point B. And this is how come driving from point A, driving from Dallas to here, even though it's something no more than 6 or 7 linear miles, it takes you at 40, 50 miles an hour, takes you almost 45 minutes. Because you have these small periods where you have to stop, exit, stop at a stop sign, stop at a stoplight. So at each place that you stop or slow down or speed up, that affects your overall average time to get here. So as that's come on land, it matters when they say, how far do I have to travel? Because instead of asking that, it says, how many stop signs, how many stoplights are there? That would tell me more than how far do I have to go. Flying is no problem. I mean, if going from Dallas to Austin, hop on and fly across. Straight line. Well, not really a straight line because you have to worry for, there are a couple of Air Force bases and military bases you have to avoid. But other than that, it's a straight line. That's why they have the ground speed, ground distances. And this is all you have to do, is find each interval that you're looking at, find that information, and then divide it overall, and that tells you what your average speed was for the entire trip. That's the last of them there. Zero negatives. Here's an interesting one. Estimate average value of the function f of x equals sine x on the interval zero pi. So how would you do this? What's the first thing you have to figure out? That? Okay, let's draw it. Very good. Always draw a picture so you have a better idea what you're looking for. We're going from 0. Let's see, we have pi over 4, pi over 4, 3 over 4, and 5. At 0, sine is what? Sine is 0. At pi over 2, sine is 1. And at pi, 0. So this is the thing we're looking for. Now, you could be tempted to do this. Take it on the right-hand side of the interval and go to the left. But what this would do is these two would wash out. You wouldn't have a value there anymore. So to make it more accurate, what you would do is, since this is our midpoint, everything to the left, take it from the right hand of the interval, and everything after the midpoint, so you're always having one type of error. So our area would approximately be sine of pi over 4 plus sine of pi over 2 plus sine of pi over 2 and then sine of 3 pi over 4. Why do I have pi over 2 twice in here? Exactly. Because on the left-hand side, I'm starting from here, going left. And then from this right-hand side, I'm starting from this side, going out. So I have to use this point again, and then this point. That's right. I'm glad you said, always draw a picture. Because when you see a picture, you can make more sense of it. Because if we didn't have a picture, we'd do left bound or upper bound or lower bound of each one, and it would be off. A lot more than we would be. So what's pi over 4? Sine pi over 4 is? Sine of pi over 2. That was square root 2? 1. Sine pi over 2? 1. Sine 3 pi over 4? Well, these are going to be the same. And they're all positive. Why? Because they're all above the x-axis. So the answer would be 2 plus radical 3. Can anybody tell me why it's 2 plus radical 3? Radical 3 over 2 plus radical 3 over 2 is 2 radical 3 over 2. 2's cancel, so it's radical 3. So that's our approximate area. Okay, let's see. That does it for section 1. Section 2, what's its title? 5.2. Sigma notation and limits of infinite sums. It gets boring writing this over and over and over and over. Especially if n was, let's say, 1,000. So what we use instead, bring back all the food, is a sigma notation. What does the Greek sigma look like? That's the sigma. I'm supposed to have little end things. This is what it's going to look like. The way it's read is the sum of f of x sub I with I from 1 to n. Yes, even though it's the Greek word sigma, in Latin, the S means summa. What does the word sum mean? That's exactly what this says. What this thing tells me to do when x is 1. So I would take my first x, put it inside my function, work it out. Then I would add my second x, then my third x, and then keep on doing that until I get to my last x as my input. And then we find the values, add them up, and that is our sigma. So let's do this one. The I is the index. It's the counter. It tells you which number are you at when you're going through this thing. Well, here are my x's. You couldn't do anything just yet because you don't know what x is. What's your input? This is my data set. This first one is x sub 1. The next one's x sub 2. The third one, x sub 3, and so on so forth. The subscripts, these are all called subscripts. They tell you the position of that value. So if I ask you for x sub 4, I'm asking for the fourth number in your data set. X sub 2 is the second number in your data set. Do they have to be in order? No, because what if you're doing a research project and these are your data numbers as they're coming in? Don't sort them, put them as they're getting in. So in most senses, if you're doing independent research, you'd have to sort them. But if in the homework assignments, yeah, it doesn't matter. But in the real world, you don't have to sort them because it's as they're coming in. So what this says is this. I start off at 1, I square it. Then I go to the next one, I square it. Then I go to the next one, I square it. Then I go to the next one, and I stop at x sub 5. Why? Because that's where it told me to stop. I'm only going from 1 to 5. So x sub 1 is 1, so I have 1 and I square it. X sub 2 is 2 and I square it. 3, 4, and 5. Square those numbers. And add them together. Yes. These are my counters. Because, I'm glad you asked. Because I could also give you this set I'm starting at my third data set. And stopping at 5. Yes, so the index begins at a certain number and ends at whatever number's on the top here. It's typically labeled as I, but it could be labeled as K also. You could also see some counters like that. But typically, we use I because it's the indices. It's the index. Sorry, guys, you missed the party, apparently. They're packing up everything. Here's some examples. Let's make it 4. Make it smaller. I don't want to keep you here all day. Do these. Let's look at some of these. What did you get for the first one? As I was saying here, starting with 1, go to 4. 4 plus 1 is 5, equals 10. Very good. And the next one, 1 to 3. Negative 1 to the power 1 of 1. Negative 1 to the power 2 of 2. Negative 1 to the power of 3 of 3. So this is negative 1 times 1 is negative 1. Negative 1 squared is 1 times 2 is 2. Negative 1 cubed is negative 1 times 3 is negative 3. So negative 4 plus 2 is negative 2. From 1 to 2, so 1 over 1 plus 1 plus 2 over 2 plus 1. 1 over 2 plus 2 over 3. You get a common denominator. 3 plus 4 is 7 over 6, or 1 and 1/6. Starting at 4. Go to 5. 16 over 3, 25 over 4. The common denominator. 64 over 12, 75 over 12. 139 over 12. Eleven 7/12. So that's how you interpret sigma notations. Some properties that, if you're ever faced with the algebra of summations, the sum rule is the first one. A sub k plus b sub k. You have two data sets, same subscripts. Since they're added together, you can treat them both separately. Take the sum individually. Same with the difference rule. A sub k minus b sub k, sigma a sub k minus sigma b sub k. The constant multiple rule some constant times a sub k. You can factor out, since each term would have the same constant when you're adding them, you can factor it out. And then find the sum of that sequence and then multiply by c. The constant value rule. There's no index on that one. It's just a constant number. What this means is you're going to add this number to itself n number of times. So the answer is simply c times n. Because remember, that's what addition really is. Addition and multiplication. If I take c plus c plus c n times, that's the same thing as saying c times n. So if you have a constant and you take it through a sigma notation, just take that value times the end result. Here's some examples. Okay, I'll use that one. rules here. That's okay. I'm sorry. Yes, it was. Since they're subtracted, you can split them up. Can we do anything else to it? There's another rule we can apply. The constant multiple, right. And there we have it. Then whatever this would be, it'd be a summation of 1 to n. Number 2. Number 2 is the same way you just said. Constant multiple. This negative is actually a negative 1. We can factor out that negative 1 out in front. Here's one that has numbers. Summation as k goes from 1 to 3 of k plus 4. So when k is 1, we have 1 plus 4. Next one, k would be 2. Third one. We're going to do it 2 ways. This is 5 plus 6 plus 7. 5 plus 6 is 11. That's one way you could have done it. Now, is there another way you could have done it using the properties? Since they're added, what can we do? We can separate them. So what does the first one tell me to do? So this one says start from 1, add to 3. So it's 1 plus 2 plus 3. That's this first part. Now the second part, this is a constant value, so we just take that constant value times whatever our n is, multiply them together. 6 plus 12 equals 18. Same thing. How about this one? What's the answer going to be? This number here. Is there an index of k in there? So it's a constant. So I can take it outside. There's 1 there. So the summation of 1 do it n times, this becomes n. N times 1 is just n. The n's cancel, so the answer is 1. There are a set of rules if it goes on for infinity, forever. Instead of trying to work this thing out step by step by step for the nth number of terms that you get, it can be simplified by having a finite formula. N times n plus 1, 2n plus 1 over 6. Likewise for cubic functions. n plus 1 over 2. All of this cubed. So it's just cubed. If I gave you this, there's 2 ways you can do it. One, you can do 1 cube plus 2 cube plus 3 cube plus 4 cube. That's pretty good. That's pretty boring after a really quick second. Or, since it's a cubic function, I could use this. Remember, this number up here is n. n, 10 plus 1 over 2. Where? The 2 and the 10 cancel. 5 times 11 squared. 55 squared. Again, it's much easier doing it this way than it is. Any change therein Is there any way we can write this like we just did? Where n is 5? N is 5. 6 is canceled, so we have 55. 3 times, so we have 15 squared. Or if you had you could do either one of those two. As long as you remember the rules of your conversions. It's almost time to get out of here. We got done with 2 sections today. Well, I know. However far we get on Wednesday, that'll be it for the semester. Whereas if you only get through 1, maybe 2 more sections, I won't test you over the rest of it. Because it's not fair, we didn't cover it. That's all my fault, because we lost too many days because of weather and my issues. So